In this video, we're going to look at the ellipse. Just like we defined the parabola in the previous videos, we're going to define the ellipse using that locus of points or a collection of points. And we're going to define the ellipse as the set of all points x, y in a plane, the sum of whose distances from two distinct fixed points called foci is constant. And foci here, that's the plural form for focus. So if you'll notice here, we actually have two foci when we talk about the ellipse. And we can see the way this is described, we have all the points x, y, so that would be all these points here that make up the ellipse all the way around. That's all of our x, y points. And it says that we have a sum of whose distances from two distinct fixed points. So our two fixed points are here, the foci. So here we have one focus point, and over here we have the other. And the fixed distance would be from one focus out to the point on the ellipse and then over to the other focus. And we can kind of imagine if you were to take a piece of string and tack it down here at one of the foci and then tack the other end of the string down at the other focus point and take your pen and stretch it out and then hold the string tight and then make your circle and go around, and you would end up with this ellipse. So what we're indicating here is the sum of this distance d1 and this distance over here d2. As this goes around, that will remain the same. So that's going to remain constant. So d1 plus d2 is going to remain constant, because if you think of stretching out a string to make this ellipse, then that string is not going to change. It's going to remain the same length. Now the d1 length as we get over here is going to get longer, but d2 is going to get shorter as we get to this point. So if we went from here to here, notice d1 is longer but d2 is shorter, so you're ending up with the exact same length. All right, so let's look at some other parts of the ellipse. If we go over here, we've already pointed out here that we have these 2 points are your foci, and of course the point here in the middle, that is going to be the center of the ellipse. And then on the end here we have your vertices. Okay, so with the parabola we had one vertex, and here we have two, which the plural form again is vertices. And we're going to notice the vertices are going to be at the end of what we are going to call the major axis. And the major axis is going to go from one vertex to the other. So this here is the major axis, and that is simply because it is the longer axis, whereas the axis going from, in this case, it's going from top to bottom. This is called the minor axis. And it's possible that the major axis, like this example, is going to be horizontal and the minor axis is vertical. Now, it is possible that the major axis is vertical and the minor axis would be horizontal. And that would be the case if the ellipse went this way. Then here, this would be the major axis, and this would be the minor axis, and then the vertices would be here at the top and at the bottom of the ellipse. Now, just like we defined some of the points with our parabola, there we were using h and k for the vertex, and we looked at using the p-value. Here, we're going to look at for the center. The center here is again going to be h and k, but now at the end we have our vertices. So here we're going to describe the distance from the center out here to a vertex is going to be a distance of a. And then if we go from the center to one of your foci, that's going to be a distance of c. And then if we go from the distance from the center on the minor axis, that distance is going to be equal to b. So what this shows us is that the minor axis, the total length would be 2b, and then for the major axis, the total length there would be 2a. So there we're going all the way across for the major axis and all the way up and down for the minor. Now, half of the major axis is A, which is going from the center to the vertex. Our C value is going to be from the center to a foci. And then B is giving us half of the minor axis. Now, in the equation down here below, we're going to understand what this A, B, and C value represent, as well as the center H and K. So let's look at the standard form of the equation. And we'll see here that we have H and K is going to represent the center of our ellipse, and 2A and 2B are going to represent the major and minor axes, where A is greater than B. So if we look at the formula, we have x minus h squared over a squared plus y minus k squared over b squared equals 1. And we know what h and k is. H and k is going to simply be the center of the ellipse. Now, the a value is the a value that we were talking about up here, which is the center to the vertex, and the b value is here part of the minor axis. So that's what we're talking about here on the bottom. We have a squared and b squared. And this is indicating, keep in mind, this is crucial to understand, your a value here is always going to be greater than the b value. So if we look at this, of course a squared is going to be bigger than b squared. So if the larger value here, a squared, is underneath the x minus h squared, that means the major axis is going to be horizontal. And if we look down here where it says the major axis is vertical, notice now the a squared is over here underneath the y minus k squared. So again, this is going to be the larger value. So the bigger number is under the y minus k squared. If the bigger number is under the y part that's squared, then it's going to be vertical. If the number underneath the x minus h, the part that's squared, then your axis is going to be horizontal. Now, we notice we have the values for A and B, but what about this C value that we're looking for, which is from the center out to one of the foci? Well, that comes from this formula here, which is C squared is equal to A squared minus B squared. Now, be careful. This looks and sounds familiar to your Pythagorean theorem, but that's A squared plus B squared equals C squared. And notice here, this is A squared minus B squared. All right, one last thing to talk about with the ellipse is the eccentricity, and the formula for eccentricity is c over a, and basically this has given us an idea of how stretched out the ellipse is. Is it more like a circle, or is it more elongated, flattened out like an egg shape? And we simply look at this ratio of c divided by a, and if c divided by a is small, and basically what that means is if it's close to 0, you're going to actually have more of a circular shape. And if c over a is closer to 1, then it's going to be more elongated. Okay, so it has a little bit more oval shape than a circular shape. So let's look at applying this to an example. Let's say that we have the equation x squared over 9 plus y squared over 4 equal to 1. And again, if we look at the standard form, realize the other part of this I didn't emphasize is each one of these is equal to 1. So we already have our standard form, and where is the a value going to be? We have a 9 on the bottom and a 4. Well, because a is the largest value, then we know that a squared must be equal to 9 because 9 is bigger than 4, so that means then that b squared must be equal to 4. So the 9 is underneath the x squared, so that means we're looking at a horizontal ellipse where we have x minus h squared. So let's write this down. We'd have x minus h squared over a squared plus y minus k squared over b squared equals 1. So what this tells us, if a squared is equal to 9, then that means a is equal to 3 and b is equal to 2. And then the other part that we need to find would be the c value. And we can calculate again the value of c by simply using the a squared minus b squared. So therefore, we would take c squared is equal to a squared, which is 9, minus b squared, which is 4. So c squared is equal to 5. So c is equal to the square root of 5. And I'll leave this as the square root of 5 for an exact answer. And if we were to get an approximation, this is approximately 2.2. So now that we have our a value, b value, and c value, now we need to determine what is the h and k. Well, remember the h and k is what's being subtracted up here, x minus h squared and y minus k squared. So down here, if we look at our x squared in the numerator, there's nothing subtracted. So what that means is this would technically be x minus 0 squared, and over here to the same thing for the y, which is y minus 0 squared. So this is very similar to what we looked at with the parabola. So here, if we're looking for the center, then the h and k is simply going to be at the origin 0, 0. So there we have the center, and then we will have the vertices. So once we know the center, we can calculate the vertices, and let's go ahead and plot that first. And again, just like we did with the parabola, it's good to draw a picture of what we're looking at. So we know the center here is going to be at the origin. So there's our center. And now we know that from the center, and again, we know this a value is under the x squared, so that tells us this is going to be horizontal. So that's important to know because that means when we go to calculate the vertices, we know the vertices are located how far away? Well, from the center to one of the vertex to the vertices is going to be a distance of a. So that means we need to go out a total of 3. So if we count over 1, 2, 3, here we will have one of our vertices, and then we'd go 1, 2, 3 in the other direction, and we would have our other vertices. So therefore, the vertices would be at, we could actually write this two different ways. We could say it's going to be negative 3, 0, and we could write positive 3, 0. And what you may see in some cases is you may see them actually write plus or minus 3, comma, 0. So this would just be kind of a short way of writing the 2 points. And then next we have this particular b value. And remember, that tells us the minor axis. So that tells us we're going to go up 2 units and down 2 units from the center. So that tells us how high up we're going and how far down we're going for the minor axis. And then if we want to look at the foci, remember the foci, that is using the center out c unit. So we're looking for the value of c. And we said our c value in this case was the square root of 5, which is a little bit more than 2. So if we go out here to 2, so that means one of the foci would be here, and then the other one would be right about here. So that's going to be located, again, if we want to get to this point, we're going out here to the negative square root of 5, and this would be a positive square root of 5. So we could simply write this as plus minus the square root of 5, comma, 0. So now we could actually make a rough sketch of our graph, which would look something like this. And we can pretend this is a little bit more of an oval shape. And the last thing we want to calculate is the eccentricity. And remember, this is telling us how circular or how elongated the ellipse is. And remember, that's going to be E is equal to C over A. So our C value is the square root of 5 over A, which is 3. And if you were to put that in the calculator, you would get approximately 0.7. And this value is closer to 1 than 0, so we can see that it is more elongated than it is circular. So there we have kind of the key points for finding the graph of your ellipse. So just as a review, keep in mind that if we're going from the center out to the vertex, then that is a distance of A. From the center on the minor axis, that is a distance of B. And if we're going from the center out to one of the foci, that's going to be a distance of C. So once again, you're going to find this to be very familiar with or similar to the parabola with the x minus h squared and y minus k squared, where for the parabola that was given us the vertex, but here for the ellipse, of course, the h and k is the center of our ellipse.